So welcome to my presentation about ZenHammer, Rowhammer attacks on AMD Zen-based platforms. So before we start, let me give you an overview about our work. So AMD has been gaining market share over the last decade, and today every third sold x86 CPU is from AMD. This, however, is not reflected in the Rowhammer attack research. There has been no attack on AMD Zen-based systems since the platform's release in 2017. Therefore, we asked ourselves if they are vulnerable to Rowhammer, and we built ZenHammer to answer this. With ZenHammer, we find bit flips on 7 of 10 and 6 of 10 DIMMs on AMD Zen 2 and Zen 3, respectively. We also find up to 46 times more bit flips on Zen 3 than on Coffee Lake, and we show for the first time bit flips on DDR5 DIMMs on Zen 4. So before we talk about ZenHammer, let me give you a quick overview about DRAM and Rowhammer. So multiple DRAM chips are mounted on DRAM DIMMs, and each of these DRAM chips consists of several banks that are organized into bank groups. And each bank is made of a matrix of rows and columns, and each cell stores a single bit of information as a charge. And whenever data is read from the DRAM device, so from the bank, or written into, then you first have to basically load the whole row into the row buffer, then you can modify it, and then you have to write it back. And if another row has been loaded before of that bank, then accessing another row basically causes a measurable delay that you can use to find rows of the same bank. And the Rowhammer vulnerability is a memory disturbance error. It happens when two rows are accessed or hammered with one row in between, as you can see here. This is the double-sided pattern. And if you repeat hammering this pattern many times over and over again, then you basically cause the charge of the victim row that is in between these two rows that you're hammering to leak, and then you will observe bit flips in that victim row. And to be able to mount Rowhammer attacks, you need to very precisely address specific rows. And for that, you need to know the DRAM address mappings that are used by the memory controller to translate the physical address into the DRAM address. And these mappings, however, are part of the in-CPU memory controller, and until now have not been reverse engineered for AMD Zen-based systems. And this is the first challenge that we tackled, to reverse engineer the secret DRAM address mappings on Zen-based systems. So we first tried the established drama approach, which consists of creating bank conflict clusters using the bank conflict timing side channel. These clusters consist of addresses going to the same bank. And then in the second step, we try to brute force the DRAM functions. So the idea there is that you try, for example, 2-bit functions. And then if you have found a valid function, then basically applying the function on all addresses of the same cluster should return the same value, for example, 0. And half of the cluster should return 0, and the other half 1. And if these conditions are met, then you have a valid function. However, with this drama approach, we were not able to recover the correct mappings. We found mappings that only worked on limited memory regions. So what we tried is to basically extend our clusters that we built in step 1 and used a memory range that is larger. And then we basically applied the function to all addresses of the same cluster. And what we found is the distribution between function values 1 and 0 is unequal. And we had the hypothesis that maybe there's some nonlinearity, and we have to subtract some offset from the addresses before we can recover the functions. So we tried different address offsets and found that here in this example, with an offset of 768 megabyte, we were able to basically have this equal distribution between the function output value 1 and 0. And using that offset, we were then able to recover the correct address function that gives a constant value over the whole physical address space. So we learned from this that DRAM functions on Zen-based systems are nonlinear and require an address offset. And this is because there is some PCI address range in the physical address space that is remapped on AMD systems. And that's why we need an offset. This offset is system-specific and can also be recovered if you have pseudo access on the system. And the second observation is that we need memory blocks larger than 1 gigabyte to recover the address function on Zen-based systems. Here you can see a visualization of one of the DRAM configurations with one rank for bank groups, 4 banks and 16-bit of rows. You can see the typical staircase patterns that we also observed on Intel systems. And you can find the results for more DRAM configurations in our paper. Equipped with these DRAM address functions, we then created a new blacksmith fork called ZenHammer, and we tested DIMMs from the 3 major manufacturers for 6 hours of fuzzing. Here we present the results. You can see that we found bit flips on half of the Zen 2 devices and none of the Zen 3 devices. However, the number of bit flips on Zen 2 systems is much lower than on Coffee Lake. And this led us to the conclusion that basically porting just the DRAM address functions is insufficient to do Rowhammer on AMD Zen-based systems. So therefore, we looked more into other possible reasons. And a major concern was that we might not bypass the in-DRAM TRR mitigations, which act at the same time as the periodic refreshes. However, TRR might not happen at every refresh, but for example, only every 4th refresh. This is why frequency-based Rowhammer patterns can also be longer than just 1 refresh interval. For example, here we have a pattern of 4 TRFI. And when hammering this pattern, we basically just repeat the pattern over and over again. And now if we just hammer non-synchronized, so we just start at any point in time to hammer, then you can see that basically the pattern shifts, which makes it easier for the mitigation to catch the aggressors. Therefore, state-of-the-art patterns synchronize with the refresh command before hammering and before each pattern repetition. This has been shown in Blacksmith and also using soft synchronization in Smash. And as this synchronization routine is platform-dependent and might not work as expected on Zen-based systems, we addressed this in Challenge 2. So we started by basically measuring the time between refreshes on Zen Plus and Zen 3. And on Zen Plus, you can see we can correctly detect and reliably detect the refreshes, but on Zen 3 we cannot. We do not get a clear signal. And now if we look a bit more into the synchronization routine, where rectangles are basically axes and triangles flushes, we can see that if the refresh happens between these 2 axes A1 and A2, we can detect it successfully. Also if it happens between the flushes, but if it happens in between repetitions of the synchronization routine, then we have basically a blind spot between these measurements, T1 and T2, and it gets undetected. And to basically solve this issue, we proposed a new continuous non-repeating refresh synchronization. This new routine basically uses distinct rows to avoid the need to flush in caches while we do the synchronization, and also uses a continuous timing measurement that avoids these blind gaps. So basically, we always reuse the last timing measurement as the start measurement of the next round. And this new routine strongly improves the refresh synchronization. So here we can see the result for Zen Plus and Zen 3. Originally, we only used 2 rows to do the refresh synchronization, and you can see that on Zen 3 it's very imprecise. But now we use, for example, 64 rows, and this strongly improves the results. Another aspect that is very important when we do Rowhammer is that the pattern length, basically the time that we have to hammer, is limited by the refresh window, which is 64 milliseconds. This limits the period that we can hammer our pattern, and also some of the accesses that we do are going to decoy rows. These decoy rows are basically to bypass the mitigations. So we need to ensure that the remaining activations that we use are sufficient to trigger bit flips. The ordering of the memory access is also important, but we kindly refer to our paper for more details on that. So we started by looking into the current activation rate with the original Blacksmith code. And what we found is that on Zen Plus and Zen 3, we only get around half of the number of activations compared to Coffee Lake. And if we now assume that we need at least 18 aggressors to bypass the mitigation, this gives us 36K activations, then this might be too low for many of the devices to trigger bit flips. So what we did is to systematically test different hammering instruction sequences. So we looked at, for example, cache flushing instructions like CL flush and CL flush opt. They can be used in a gathered style, so we access all the aggressors and then we flush all of them, or in a scattered style where we do access flush, access flush. We looked at different memory barriers, different access type, and also different vector instructions. And here I present the results. So we can see that with load instructions and scattered flushing with S fences or using no fences at all, we achieve the highest number of activations that are theoretically possible. We also found some of the cases where we observed cache hits, which is undesirable for Rowhammer, right? Because you want to always go to the DRAM device. And to evaluate the effectiveness of our optimizations, we then sweep the best pattern that we found in a 6-hour fuzzing run over 256 megabytes of contiguous memory. And we can see that these optimizations drastically improved the number of effective patterns. On Zen 2, where we found bit flips on 5 devices, now we find bit flips on 7 devices. On Zen 3, where we did not find any bit flips on none of the devices, we now find bit flips on 6 devices. And we also have a higher number of bit flips in 4 cases on Zen 2 and in 5 cases on Zen 3 compared to Coffee Lake. We also have one device, H0 from USENIX, where we found bit flips where we could not find any bit flips on Coffee Lake. And we also analyzed the impact on the exploitation. Please see our paper for the results. We also reproduced an end-to-end PTE attack on AMD Zen 3 because we had to address a number of challenges due to the different DRAM address mappings on Zen 3. And we ended up with a reliable end-to-end exploit, flipping bits in a page table entry to get an arbitrary read-write primitive. So here I prepared a short demo for you. So at the beginning, we just show that we are a regular user. Then we load a pattern that we found before during templating on the Zen 3 machine. We allocate different memory regions for the refresh synchronization and the hammering. Then we do the coloring, so we determine the DRAM address mappings within the transparent huge page bits, and then we start hammering. And every time we find bit flips, we try if the pattern is repeatable. And once we found a pattern that is repeatable 5 times, then we spray the PTEs, we repeat the bit flip, we check which of the mappings get corrupted, and then we open a root shell. During the rebuttal, our reviewers also asked about Zen 4 and DDR5, which we did originally not consider. So we repeated all experiments on Zen 4 and tested 10 random DDR5 DIMMs, and we found bit flips on one of the devices. So generally, it seems like DDR5 is more resilient against Rowhammer, but we think that more research is needed to understand their susceptibility better. To conclude, we showed that AMD Zen-based systems are equally vulnerable to Rowhammer as Intel systems. We disclosed for the first time the secret DRAM address mappings for Zen 2, 3, and 4, including their offsets. We showed bit flips on 7, 6, and 1 DRAM devices on Zen 2, 3, and 4, respectively, and the first DDR5 bit flips. We also showed up to 46 times more bit flips on Zen 3 than on Coffee Lake, and we showed how this high number of bit flips translates to exploitation. And in the best case, we only need 6 seconds on Zen 2 and 2 seconds on Zen 3 to mount the PTE attack. And we also reproduced the PTE exploit end-to-end on Zen 3 to show how the changed DRAM address functions affected. Thank you very much for your attention. I'm happy to take your questions.